We can do that with some chairs. So the exam is not open note. It is in person. I have forgotten that some of the lecture videos are referencing COVID area when it was all online, and there it was open note. Believe it or not, it is to your benefit for it to not be open note, because every open note exam I have ever given has dropped the average significantly. I'd say on average at least 10% drop in student performance when it's open note. Yep, every single time, multiple different classes. It's shocking. And 10% average is the average result usually, or the more common ones I've seen are usually on the upwards of 20 or 30% drop in performance on the exams. And to me, the biggest reason for that is that people get over-reliant on their notes, thinking that their notes will give them answers. Nothing we do in OChem is fact-based. Everything is application, which means your notes are only useful if you have the answers to the questions. And if you had the answers to the questions, you didn't need the notes because you already had the answers. So notes become way too heavily of a crutch that actually causes more failure, which is interesting, but that's how it seems to pan out. And I think the biggest difference is that OChem, more so than I think any other subject, even in general chemistry, requires application to a new structure, a new way of looking at things. And it's that application part that your notes just don't have. So you pick up the fluidity to be able to be successful through practice. That's where it comes into play. So there's that part of it. The other part is that they will be in person. And if we push to the online, even with the online exams, when we were COVID era, those averages dropped from in person. And I mean, I think that's even more shocking because, to your point, you aren't trying if you aren't cheating. And cheating had to have been rampant online. So to see the average drop even more so with that is, I think, kind of astonishing. So yeah, in person, it will be next Thursday. We show up and we'll start right on time. I'll try and run it based off of my clock, not off of that clock, but then probably end it based off of that clock. So you get a little bit more, a couple more seconds effectively. You are allowed a model kit. You should be bringing your model kit. I will bring a couple spare model kits. But yeah, trying to build a model during the exam is the wrong idea. That's just not going to work. So you should show up to the exam with a cyclohexane. I'll crudely draw it. So you should have a cyclohexane and then another carbon, and then that carbon should have hanging off of it a red ball, a blue ball, and I think fairly commonly a green ball. Okay. That single structure now allows you to answer virtually any question. Okay. If you use the Darling models, it's significantly easier because it allows you to see kind of the Newman projections and all of that. If you're using the gray boxes, your modification is that you have to add bonds for all of your frickin' hydrogens so that you can then see all those. Okay. That's why the Darling model is better. So you don't have to build those all out. Right? But that now has relatively pre-built, should allow you to be able to answer almost any question based off of any of those kind of systems. Right? And we'll talk through some of what that red, blue, and green can mean, both when we talk about chiral and when we talk about, I think when we talk about chairs, yes, when we talk about chairs, we can drop it in there, and we can talk about it a little bit when we talk about our Newmans with our Gausches and all that. Okay? You are allowed a calculator as well. I really don't think a calculator is useful. Like, I'd be surprised if you even turn it on. Like, that's how useless it is. The next exam maybe becomes a little bit more useful, but if you know your multiples of 12, you'll be fine. And if you don't, that's okay too. I struggle with it as well. Okay? Oh, I forgot to look at how many short answer there were. I think there's 36 multiple choice, and there's usually 5 to 6 short answer. Short answer starts the exam. Where should you start the exam? What's that?
Wherever we want.
Do better. Wherever you want is pretty good, but I think you should be able to do better than that answer.
Where we're comfortable.
That's a little bit better. Wherever you know the answer is where you should start the exam. Make sure you get the things you know down correctly. Okay? And that is different for everybody. The exam does get effectively randomized, so you could encounter right away stuff on chirality. That was the most recent stuff we talked about. Or you could see Lewis structure. Okay? So what you should find is the places that you're comfortable. Anything that you look at and you're like, this isn't comfortable, move on. Okay? Eventually you will have to come back to it theoretically. Okay? But move on from those, because if you're uncomfortable with it, the odds are already against you that you are going to get it wrong. Spending any time on it right away was a waste of time. Okay? And that's triaging. And as much as there's debate over having long exams or short exams or anything along those lines, life is about triaging. Okay? It is a necessary skill for you to pick up. It is something that you should learn, and exams are the perfect place to pick up that skill. Okay? Yeah, I think that covers exams. Does that answer your question well enough?
Yeah.
As far as exams go?
So next week it'll just be like questions on whatever, same things you ready for the exam.
So our lecture periods are pretty much the same all the way through. It's up to you to decide what you have questions on. The content is already set up and delivered online. It's you finding your weaknesses to get those effectively exploited in class, okay, in a rather public display of, I don't know how to answer this question. Okay, let's talk through it. Let's figure out how and why. So that when it shows up on an exam, you know how to deal with it.
Dumb question, but is yours lab next week?
Yes, there's lab next week. I do try to set it up so that the labs are less painful on exam days. It's not perfect, but I would argue the lab next week isn't a horrendous one. You can do that mostly brain dead. Mostly.
If I feel like I don't need to sit through the whole lecture, is it okay if I leave a little bit early?
That is absolutely okay with me as well. The only note that I would say with lecture attendance is you let me know. Because if you ghost, I don't know if you're here or not, and I have the ability to withdraw you. So if you decide you need to take off, you've got emergencies, phone call, that's fine. Just send me a message, let me know, and that's it.
So like if I want to leave early today, then do you know right now?
No, today, no, you can't leave early. Yeah, that's fine.
Okay.
Yeah. And yes, now I know, you're fine. You got to take off, take off. Next question?
How's your day?
Not an exciting week.
Sorry.
Driving rental cars and sick kids,
Oh, man,
So.
I'm sorry, it sucks.
which I'm sure everybody experiences.
I don't have a kid, but I have a dog.
It's close enough. Did I record that? Yeah. I just won't tell the family about that. So I believe chairs is what we're asking about with that. Do you have specific questions about chairs? Like I can do kind of a big overview kind of thing.
Yeah, just because like the axis and axle and all that kind of just got kind of
Dealing with you? Okay.
Cool names.
So we'll try and hit with a kind of sort of basic overview. If we were to look at cyclohexanes, and for those of you wondering, that screen was flickering, so we're not using it. We look at a cyclohexane, 6 carbons in a ring. Our 6 carbon in the ring structures have some interesting properties. If you start with a 3-membered ring or a 4-membered ring, and you try to build those, what you find is they just kind of snap together and they're locked in that space. The instant you move to a 5-membered ring, what you'll note is it has a little bit of flop to it, a little bit of wiggle. Okay? And if you move to a 6-membered ring, it has even more kind of wiggle and looseness to it. Even with the 5-membered ring, with that flop, you'll still feel some tension in the model. Okay? The 6-membered ring, all of that tension disappears. Okay? And you can hit spots where it's now super stable. Okay? Those super stable things kind of mess with our way to draw and represent them. Because what we're talking about is that wiggle and flex within the model, which then means none of the atoms, well, not none, but most of the atoms are not in the same plane because it tweaks off axis, which means our drawing of a cyclohexane isn't accurate. Okay? So that's where we shift our view and say, well, how could I draw it to better represent the three-dimensional object? Okay? And in that representation is where we ultimately get our Newman projections. Sorry, not Newman, chairs. Okay? So if we were to draw your chairs, the first thing you should do, so this should be not new to Tuesday or Wednesday, Thursday lab, we'll talk about this again. For our chairs, we want to draw our seat, which is 2 lines kind of parallel next to each other, because if we had a chair, right, okay, and we try to draw it 3 dimensions, you might see the seat kind of come into existence there. That's what we're trying to represent. And then there's the other chair leg. Maybe there's another one back there. Okay, that's what we're trying to set up, is that space for our chair. Okay, the next part that we would go through and do, crudely, center of mass, cut that structure in half, or cut those 2 lines in half. So when we now look to the left half on this side, which of those lines is the shortest, the top or the bottom? The top. So from that top line, I now want to go up. Why up? It's the top line. That's where it's coming from. Okay? I can then connect to the other line. We look to the right half, and we do the same argument. Which line is shorter, top or bottom? The bottom. Since it's the bottom, I will now draw down, trying to create my triangle, and then I connect back up. And what I've now drawn is my chair. Okay? What this is trying to represent is the cyclohexane in its 3-dimensional shape. That's the whole point behind this. Okay? Trying to see and find the chair is challenging, okay? But it is something that becomes important, and it allows you to actually navigate and deal with all the different representations that come out of it. So if we were to go through and look at a cyclohexane and we just looked at it from the top, we should theoretically be able to see the hexagon and be okay with that. You know, well, it looks like it's all in the same plane, particularly if you're far enough away from me. But if we turn and look at it from the side, we can tell that they aren't all in the same plane. Okay? And we might be able to say, well, it's a zigzag. Okay? Yes, but then that also changes our viewpoint on it. So someone sat down and just looked at it enough and said, eventually, they achieved something along these lines where they're now like, oh, I have a chair. Okay? And that chair definition is a bit wonky, okay, admittedly, but that's what they're seeing. The chair where you would put your back, where you would sit down, and then where you put your feet. Okay? That's what the model is trying to represent. If we were going through and looking at the drawing, we have the same kind of thing. This area would be our seat. This is where we would put our back, or what I typically reference as a head. And then at the other end, we've got where we put our feet or our legs. Okay? So it's effectively a lawn chair, kind of reclining back. Kind of, sort of? Okay. Within this structure, we've got a couple interesting observations. Where's our chair facing? In that way. So theoretically, I've got the model set up the same direction as what's shown on the screen. And what we should note is that I can rotate bonds. So and as we do that, you'll see some things pop. I'm not really forcing it to do anything other than just do a slight rotation. And as I do that, you can see that front one like snap kind of into place, because what it's doing is alleviating the strain within the ring. Okay? As you continue to look at it, you can see varying shapes that come out of it. And your textbook and the internet will talk all about all the varying shapes that come out with it. There's the boat, there's the twist boat, there's the flipping whatever, and ultimately I don't care about those. because all of those are higher energy states. Really the only one that super drives what we want to deal with is our chair. Okay? But why is it super important to talk about all those other shapes? Well, I can take my lounge chair, just like a normal lounge chair or fancy lounge chairs, and decide I don't want to face towards the pool, I want to face away from the pool. And because I'm lazy, I don't want to pick up and turn the whole chair, I can take the head of my lounge chair and drop that down, and I can take the feet and pull that up, and now I'm facing the complete opposite direction. We can do the same thing with our models. We take our head, we drop it down, creates that weird pop, okay? And we can take our feet and we can pull them up. And now our chair is facing the complete opposite direction. Okay? What we're responsible for is acknowledging that that happens, which also generally means we need to draw it. Okay? If we're going to go through and draw it, we're going to set up a similar system as we just went through and did by drawing our seat. Except now, instead of our seat kind of sloping upwards in the vision we're going, we want to face the other direction, which means my seat needs to slope the opposite direction. I'd go through the same process, shorter, there's my green pen, longer, shorter, longer, and I have another chair where if I'm now sitting in this, I'm facing this way. Everybody kind of see it? Okay. The reason for why we look at those two pieces is going to come into play. Where are you facing? Right? That way, if we now add a different atom to it, okay, and that atom is going to help to accent some of this interaction that we're going to talk about. So I'm just going to put it there. Okay? That atom is relatively aimed up, down, right, from our ring. Okay, so our ring being kind of a plane moving through, and we've got the atom straight up. If we go through the ring flip, I take my head, pull it down to become feet, take my old feet, pull it up to become a head. Okay? Atom's still connected. Is it in a different space relative to the ring? Okay. Hopefully what you can see is it isn't on this up-down anymore. It's on this kind of horizontal space. One might call it the equator of the molecule. And that's where the name for those positionings are now coming from. This position for that substituent is now known as equatorial because it's on the equator of the molecule. If we go back through that ring flip, it's no longer on the equator of the molecule, it's going up, down. So we would call that axial. Okay? And you'll note that I say up and down. That's only going up. Or it's going down, depending on which perspective we're looking at within the molecule. Kind of, sort of? Okay. Which is then going to set us up kind of with the next potential thing. Okay? If I go through and do this, I'm axial, up, I do my ring flip, and I'm now equatorial. Every time I do that ring flip, what happens to my substituent? Yeah, it's no longer axial, it becomes equatorial. What happens if I do another ring flip? It goes back to axial. So every position on our carbon ring is going to have two bonds. Because it's cyclohexane sp3, there's two atoms or two bonds hanging off each of those carbons. One of them will be equatorial, one of them will be axial. Right? We can see that visual difference, so maybe that's why we're talking about it. Right? That helps us to kind of reference it. Right? But is there something more important than just that it visually looks different? Right? Most of organic chemistry isn't that it visually looks different. Right? It's that it has a different energy associated with it, because that makes it progressively either easier or harder for us to go through and do. Okay? So a lot of chemistry is just how do I move to look like something I want it to do by moving through different energies. So now I have to understand, is there an energy difference between these two? Okay? Well, is there a way to look at a structure to understand something about energy? Yeah, what is it?
I don't know, just thinking Newton equation.
Say it again?
Newman projection.
Okay. We had our side view, which just made it nice and pretty. We could see all the atoms nice and cleanly, and we've got our structure. Okay. We then moved it to the Newman projection, looking at it end on. Okay? That really only gave me information about a single energetic of the bond that has now disappeared. That's it. Okay? But it's giving me energy information. If we're looking at the ring, guess what we now need to do to decide something about energy? We need to find the Newman projection of our ring. Once we've found the Newman projection of the ring, we can now ask the question about axial versus equatorial. Is there a difference in energy? Okay? That's what the lab assignment is trying to make you do. Okay? Fun thing about the ring is your Newman projection means you're citing down any one bond. How many bonds are in your cyclohexane? A couple different answers I would accept with that. I kind of accept a lot. I was hoping for a little bit more quantified. I would go with 6, okay, within the ring. Okay? You could then also tack on that each of them have 2 extra things hanging off. 12 and 6, so 18 different possible Newman projections. Well, which of those Newman projections are relevant to us? The only Newmans we're caring about is where our group, our substituent, is in the Newman projection somehow. Well, what defines in our Newman projection? If we were to look at that drawing of a Newman projection, what atoms are in the molecule? Just made it a little bit easier. What atoms are in this molecule of my Newman projection?
Hydrogen, bromine,
Solid.
carbon, yeah.
How many?
1 carbon, lots of hydrogen, no bromine.
1 carbon, 2 carbon, 3 carbon, 4 carbon. Interesting. We're getting a whole bunch of different numbers coming out of this. This becomes some of the implied information and explicit information that we have to watch out for. 1 carbon, probably because you saw the C. 2 carbons, because you saw that that point is now a carbon. 3 carbons, oh, I've got the one in front. 4 carbons, the circle in back was another carbon. Ooh, all of that information is encoded within the drawing. We have to be very careful to not lose that information as we translate through. Make sure I didn't lose anything. 1, 2, 3, yeah, we should have 4 carbons. Okay, we do have 1 bromine. I really don't want to count all the hydrogens, but I started the problem. I guess I got to finish it. 2 and 3 is 5, 6, 7, 8, 9.
That looks good.
Okay, so we have all of those atoms are in the molecule. Which of those atoms are in the Newman projection?
All of them?
Okay, all of them. If all of them are in the Newman projection, let's refocus back to what the Newman projection's goal was. What is the point of the Newman projection?
So you see the energy level?
Energy levels. Is this bromine contributing to the energy levels of the Newman projection?
Yes.
Okay. How do we know the different energies of our Newman projection?
2 close to each other?
Yeah, eclipse and staggered.
Eclipsed or staggered. Okay. What are you talking about when you're talking about eclipsed or staggered?
Eclipse is higher energy but less stable.
True. So yes, eclipsed is higher, but what are you looking at to say eclipsed is they're overlapping? What's they? What is overlapping?
The electrons are too close to each other, so they're
What electrons?
a bond.
Those bonds are the ones we're referencing in the Newman projection to get us the eclipsed or staggered. Is the bromine connected to one of those bonds? No. Is the bromine in the Newman projection? No. It's in the molecule. It's not relevant to the Newman projection because it's hanging off of the structure in a not relevant position. Our Newman projection is solely the bonds of that red system. Okay? That's what tells us the difference between eclipsed versus staggered. Are there different staggards?
Yeah.
Yes. What are you looking at when you look at different staggards? Distance between what? Me and the wall? What's anti? Ooh, there we go. There's an important word. The atoms. Which atoms? Do I care about the bromine atom? Why not? It's not part of that Newman projection. The only thing I'm caring about are those atoms, and technically that C and that C. Those are the atoms of my Newman projection. Those are the ones I care about. And when I look at those, I can now go through and define that structure as gauche or anti? Gauche. Why are you calling it gauche? These two groups are closer together. Why did you not talk about these two hydrogens? A right idea, I should push on that a little bit. Are these two hydrogens on the side gauche to each other? Yes. Absolutely, they're in that space. Why aren't we calling that gauche?
Not important.
Why is it not important?
Hydrogen, so we have a lot of those.
Sort of, kind of, yes.
Why? It's a low priority.
What? How do you define priority?
Electrons.
Is that what you guys mumbled back there and you didn't say loud enough for me to accept? Okay. Our carbons have more electrons than the hydrogens, which means when we're going to look at the overall energy of this diagram, we're going to look to the greatest contributor. That's going to be the carbons butting up against each other, not the hydrogens. If you go through and do rotations, guess what? You will always have hydrogens being gauche to each other. They do contribute to the overall energy. Is it contributing anything new in each of those cases? No. So what do we call that energy? Zero. We ignore it. And our only focus is looking at that higher energy difference.
So
Okay.
So those two carbons together is gauche, meaning it's too close, right? That's supposed to mean?
It doesn't necessarily mean that they're too close. It just means they are close to each other, and that creates a higher energy state than if they were far away from each other. Right? You can absolutely quantify it. I don't want to quantify it. If you want to make me quantify it, that's office hours. I'll be grumpy.
On Tuesday, we were going over the same thing for your lab, and I remember I thought I had it because I said, hey, they're far away from each other, and you said, no, they weren't. No, you said they were far away, but it doesn't matter because they're on the same plane.
So we have to decide, what we were talking about there, what is the relationship between those green hydrogens? Are those anti?
Yeah. Those two.
Are those anti?
No.
Why not? What is anti?
Antis when they're opposite each other.
Opposite each other. So if I go opposite that bond, I'm out over here. Is that where my other hydrogen is? No. Okay, so it's not anti. Is it gauche?
No.
Okay, what's gauche?
They're next to each other. Or
That would
it's the
be
Newman projection.
here. So it's not anti or gauche.
It's just there.
It's just there. Why don't we name that? When we're talking about Newman projections, we're talking about the different energies when we rotate the bond that we can't see, right? That's that bond in back. Right? Okay, so there's a Newman projection. We're talking about the different energies when I rotate. Oh, that's high energy, high energy, high energy. Oh, less energy, less energy. Okay? And what we just talked about was, come on, get in there. Gauche, right? Gauche. Ta-da, gauche. Okay? That's not great, because it could be better if I was here. Okay? Am I asking about this relationship or this relationship? Well, this one in the gauche is what we're calling this orange one. This blue one is that one. Anti, and it's not that either. So where is that one? What?
On the carbon in the back.
Turn around. Okay. It's on the carbon in the back. So instead of rotating the front, I'm going to rotate the back. Tell me when the distance between those two atoms changes. It stays constant the whole time because they're connected to the exact same carbon. Which means no matter what you do, whatever that interaction energy is constant. And if it's constant, what can we call it? 0, we don't worry about it. Okay? I believe that's what we were talking about, Adolfo, is it's connected to the same carbon. Is that obvious in our diagram? No. Is it cleaner to see in the model? A little bit. Okay? But that's the part that we have to recognize what's happening within them. Kinda, sorta?
Yeah.
Sorry. Did not figure out how to connect. Okay. So now, hopefully, we're mostly squarish with Newman projections. Okay. So where we started is what's in the Newman projection. That was only the red atoms that we cared about. Now the green ones I've kind of overlaid with the red. Okay, those are the ones that are directly contributing. So when we go through and look at our cyclohexane, we've got a bit of a problem because we said there's 18 bonds I could look at for my Newman projection. Okay, and I don't know about you, but 1 out of 18 isn't good odds to find the correct one to look at. Okay. So are there any I could eliminate? Does it make sense to look at the Newman projection where this bond right here between the carbon and the hydrogen disappears? Why not?
Because you maybe 3 bonds will be overlapping or something like that. It will be better maybe you have the substituent, like the bond closer to the substituent, like something like that. I don't know what to do.
Your wordings is pretty good there. What was our whole point of using the Newman projection on our rings? What were we trying to find? Energy level of what? Yes, do better. Yes, of the substituent. The energy level of what is relative to the substituent? Easier words to say than substituent. Stop making me say it. It's 2 words. One is A, one is E. Axial and equatorial. That's what I care about. I don't care about any of the Newman projections in here that don't show the substituent in the Newman projection. I need that. Okay? And this is where we have to be careful on in the Newman projection. So how about this bond right here? Everybody see the bond I'm pitching? That bond? Should I look at that bond? Does that put the atom, our substituent, in the Newman projection? That's a real hard question. We're getting a lot of yeses. When we looked at our important things, what is going on with my screen? Oh, fudge me. I just got to erase it all. That was what? CH3H. What were the things that we said were important? Walk me through it again. Is that what allowed me to say eclipsed versus staggered? Referencing this C and this C is important. Absolutely. That had nothing to do with eclipsed and staggered. What did that have to do with? Gaussian anti. So yes, that's important. You're answering a question I'm going to ask in like 30 seconds. Bond, 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 bond. That's what's allowing me to see eclipsed versus staggered. I'm looking at the bonds. How do I know gauche versus anti? That's now all the atoms around it. And herein lies the fun question that I just asked when holding up the model. If I look at that bond and make it disappear, is my substituent in the Newman projection? Is it one of those important atoms? And we got some people aggressively saying yes and some people now cautiously saying no. When we highlighted the atoms that were important, did I highlight the front carbon atom? No. I highlighted the bond. I did not highlight the front carbon atom. Did I highlight the back carbon atom? No, because those aren't relevant to the energy of my Newman projection. The energy comes from looking at the bonds and the things hanging off of those. So if we go back to my structure, the substituent is incredibly important to include in my Newman projection. There's a bond there, but that places now that atom, my substituent, as the front. Or if you want to get real fancy, you can make it the back. It doesn't really matter. Either way, neither of those are in the Newman projection. So I don't like any of these hanger-on bonds. I don't like this bond. How about this bond? Now when I look at that bond disappearing, I'm looking at that carbon. If we spin this around a little bit, that red atom is now effectively my fudge, come on. Sorry, I had it right the first time. I thought it was in the back. That red atom now is connected to the front carbon. I can now reference its importance to the rest of the Newman projection. Kind of see it? And if you're looking at people over here are looking at oh yeah, it makes sense. And the people over there are like, what the hell are you talking about? It's directional. I'm sorry, I can't point everywhere at the same time. Are we kind of getting it? Yes?
Or can we always assume that the atoms in Newman projections in the center are carbon?
You can't always assume. They are most commonly carbon.
Okay. How would we indicate it from not?
How do I know that center atom isn't a carbon? I want to make it a nitrogen. How do I make it a nitrogen?
Well, you can put it.
Yeah, it doesn't have to be hard. Yeah, that's all it is. Okay, but it's not N. Knock it off. Okay, so there we go. Cool, we now have a Newman projection that we could look at. Okay, and now when we look at this, we could now start to evaluate the energies behind this. Okay, so now what we want to do is consider all that information that we have from Newman. Okay, we had eclipsed, we had staggered, we had anti, we had gauche. And we now need to overlay that on top of what we're looking at. Okay, is eclipsed relevant for that Newman projection? Do the bonds overlap each other? No. So it ain't eclipsed. So what's next? It's staggered. Okay. So staggered, great. Problem with staggered is what does staggered do?
Stagger.
Subdivides into two categories, be it gauche or anti. Okay, so yes, it is staggered, but now I'm really concerned about where that group, what is it interacting with that could make it really high energy, like gauche, or lower energy, anti. So what am I comparing my hands now to? I think I said that as a question, right?
The carbon?
What carbon?
The one, I was gonna say the carbon.
I don't care about over there. I care about here.
Oh,
Is it this carbon?
no,
That one?
no,
Is it that one?
no.
Is it that one?
Can't tell, honestly.
You just said no to all those and you can't tell that one.
Oh, I can't tell if it was the first one or the second one.
Oh, fair play. That's a distance thing. Get your eyes checked. That was a joke for the record.
Yes.
What are you saying?
Upper left.
Oh, you mean the one I haven't pointed to yet? Yeah. This atom right here is the front atom. That's not an atom relevant to the energy of my Newman projections. This atom here is the back atom of my Newman projection. That's not relevant to my Newman projection. Okay? This atom is. That's the one hanging off. These two aren't in the projection at all, so I don't care. These two out here are effectively my bromine. I don't care about them. What about this one? It's progressively getting harder and harder to hold up. What about this one?
Unsure.
It's connected to the exact same place where my substituent is, which means if I do any rotations, what happens to the distance between those? Stays the same. If it's the same, that's constant, there's no effect.
Yeah.
The only one that would then fit leaves us with this, which means that's the one we should talk about as far as an energy. Well, is that anti or gauche? That's gauche. Right? And if we're talking about our axial versus equatorial, we now need to layer that information in. We're saying that that interaction is gauche. For what substituent on my chair? Axial. So remember that chair stuff, I have to hold all that chair stuff until I get the Newman to now overlay with it. So that axial generates a gauche interaction with the ring. The whole point of this was to see both chairs. Because what could I do with the chair? Now I go back and do the exact same thing looking at my Newman projection and I say, what happened? It's equatorial, I accept that, and anti. I can reference the exact same atom if I'm holding it in the exact same space, and I can now look at those relationships, and they are now opposite each other. So in one chair conformation, I had axial and gauche. The other chair conformation, I had equatorial and anti.
That carbon that you're talking about, the one that's more important, is that the same carbon we see up there on the Newman projection?
Same carbon's a bit of a misnomer because this has bromine in it.
It's the one connected to the bromine.
Okay, but the relationship between the one connected to the bromine and our CH3 in the drawing on the board is the same as our red atom in the CH3 and the CH2 I'm holding.
Right, it's just kind of hard to visualize how they're actually like my hands and like so.
Yeah, that's why we do a model lab.
Right. So it'd probably be more helpful if we had like maybe like another red or something to connect it to. Or
Thought there was one.
Any color, honestly.
How about blue?
Perfect. It's just hard to visualize the actual
Oh.
space between them.
Oh yeah, I get you. It's a good idea. If I can get it to connect again.
So basically what you're saying is they only matter because it's carbon, because they have higher energy, and so because it's higher energy, we're focused on those, and it's the only one that can actually rotate versus the other ones can't.
Yeah, these positions
Yeah.
don't change relative to the red one. I can do whatever I want. It's never going to change because they're all connected to the same spot. This carbon back here is also connected to the same carbon,
Yeah.
so its position is never going to change. The only thing that's going to change is out here. And only is a bit of a vague term. We're going to come back to that in a second.
Okay.
Right? Because it does get a little bit worse here. Okay? So we walk through. We'll rewind back just a second before you asked your question. Equatorial gave us anti. Everybody see the color alignments? They're on opposite sides of our carbon structure. We go through the ring flip. This blue thing is messing with my ring flips. Okay? Now we have axial, and our interaction is gauche. Everybody got it? Which did we say was higher in energy?
Axial.
Gauche is higher in energy. For those people saying axial, I understand where you're going, but axial versus equatorial never makes a statement about energy. It doesn't. Newman does. Newman says those are gauche and therefore higher in energy. Because this is the higher in energy state and that happens to be axial, Axial I can now say is higher in energy.
in this instance.
Wait, but doesn't it make a statement on stability, therefore also energy? 'Cause now
When
this-
could you make the statement on stability? From the chair or from the Newman projection? From the Newman projection. Axial is not defined in the Newman projection. Axial is defined in the chair. So it's when you're making that claim. We cannot make a claim about energy with axial and equatorial until we address the Newman projection. Once we've addressed the Newman projection, now we can ignore the Newman projection and say axial is higher in energy. Okay? Does that kind of make sense?
Click it
It's
off.
how you stack that information. All right, what happens if we moved it and did the ring flip to the equatorial? Now it's anti. Well, anti is lower in energy than, so many different terms. Than gauche, thank you. Which therefore means this configuration is lower in energy. This configuration has my substituent in the equatorial position. So now I can make the statement that equatorial is lower in energy than axial. That statement is only valid because of Newman projection. That's it. Right? This is challenging to manipulate and see those systems. What most people will end up just memorizing is that axial is less stable than equatorial. And if you do that, you're good. It's no longer a 50-50 because I'm not saying which one's which. I'm just saying I know axial is less stable. That means higher energy. And if you memorize that, you're good. Unless I ask the question why, and well, then you got to draw all the Newman projections. Could you expect to see a why question? Yeah. Right? Would that be in the multiple choice? No, that would be in the show your work. Right? Is it part of our content? Yes. Do I expect everybody to get it, understand it, manipulate it, and own it? No. Right? So I would expect people to potentially get that wrong who didn't own the material. They deserve a lower grade than people that did. Right? Doesn't that make logical sense?
Give it some credit.
Right? That's the intent behind it. Even then, you're talking maybe 6 points on one test. Is that 10% of your grade? No. So what does that mean? You don't have to know all the whys, and you can still get an A. But I have to provide the opportunity to allow those students who really know it, show that they know it. That's the intent. Sorta? Okay. There's a fun question. It's always fun. Fun question in the smart work that says for this given structure, how many gauche interactions are there? Right? And more than likely, I don't remember the actual thing. More than likely what you're looking at, I think Abby was the one looking at it, so maybe you can correct me, is you're looking at something like this. How many gauche interactions are there? Eyes bugging out is okay. When do you see gauche interactions? Do you see gauche interactions in an overhead view? Do you see it from a side view? You see it from a Newman projection, which means get it into a frickin' Newman projection so you can evaluate the system. Okay? Might regret that blue here in a second. Hopefully not. Do you agree that that's the chair we're looking at? Okay, I need to stop aiming it at her because she's answering everything real fast. Right? Does everybody agree that that's the chair we're looking at?
Is it? Wait, where's the red at?
The red? Ooh.
Is it back? Yeah.
So what does that mean?
Back.
That should be our chair.
Yeah.
Good catch. Why? So when we look at the chair, the lower bonds are the ones that are in front, which means this carbon and this carbon are in front. These carbons are in your front view. Is there a methyl on either of those carbons? So to Adolfo's point, I shouldn't have had the methyl there. I needed to have the methyl on the back carbon. That's our higher line. Right? So we're now looking at, if I can keep this all straight, okay, at our chair. When we're asking this question, they aren't saying do a bunch of chair flips. So don't chair flip it, leave it static and say, okay, what do I have? Right? And we want to evaluate all those interactions. What kind of interaction did we see when we had an axial? Gauche. What kind of interaction did we see when we had an equatorial? Anti. So if we look at this, our first answer might be how many gauche? 1, because I have an axial, and I have 1 anti, because I have an equatorial. We punch it into SmartWork, and SmartWork says you're wrong, because you are. Okay? Why are you wrong? Okay? And this is where we're going to have to be real careful with this kind of spatial awareness. I'm going to do the best that I can to show you this. Okay? Where's the Newman projection you want to look at? I don't know why I asked that question, because I don't know that there's something that you could say that would allow me to get to it. Okay? We're going to look at this Newman projection right here. I want to sight down that bond. So slight rotation. Vaguely see the Newman projection? Oh, I think this will work out nicely. We'll see. Okay? Where's the Gauche interaction with this red atom? And I accidentally set you up with a whole different answer. What's that? Is the blue one in the Newman projection? No. So I don't accept the blue one yet. Where's the Gauche interaction with the red atom?
That black one sticking out.
The black one sticking out. The black one sticking out was that substituent.
Yeah.
You mean they're interacting with, but they're so far away from it. They're so far away from each other in the drawing. You have to realize that that space in the drawing is artificial. Those are Gauche. Okay? That was a Gauche we didn't count for, which means our number should go up to 2, but where's the one that you counted initially? What did you say? On top? On top? Say yes. Yes. There's your Gauche interaction. That's the Gauche interaction between our axial and the ring. That's what we just walked through. That's the Gauche interaction. By drawing this out or building the model, we now see another Gauche interaction. The two substituents are Gauche to each other as well. Okay? So we could be like, oh, I discovered a new thing. This means I must know what I'm talking about, and I put 2 Gauche interactions into SmartWork, and I click submit, and I'm again wrong. This is a Newman projection, right? What is this? Another Newman projection. And in that other Newman projection, do you see another Gauche interaction to the blue atom? Every axial has 2 Gauche interactions with the ring. Okay? Hand cramps. So that when we look at this, that's axial, 2 Gauche. How would I know this equatorial interacted with that axial? I would argue you have to build it. All right, that's my opinion. If you're one of those spatial wizards and can see that, great for you. Okay, good luck trying to teach anybody. Okay? So that particular system gets us 1 Gauche interaction in that Newman projection. There's nothing else because we have hydrogens and hydrogen. We can turn and look at the other Newman projection. There's the Gauche interaction with the other atom of the ring. and a Gaussian interaction with the other substituent. So this particular drawing had 3 Gauss. If you now go in and say, my answer is 3, be flippin' careful. I don't know that's the same structure. Okay, make sure you're looking at the right structure. Kind of, sort of?
Yeah.
Can you turn this little blues towards?
Okay, so there's our 1 Newman projection. There's that other Newman projection. Okay. Officially, there's just 2. Okay, but if you wanted to get real nasty on this, you could say, well, isn't that also a Newman projection? Yeah, that's just the mirror image of the one I just had. Okay. So when you look at a structure, technically you could draw 4 sort of different Newman projections, but 2 of them, they pair up to be equivalent drawings. Okay? This is painful a little bit? Yeah.
This needs practice.
Does this help with your chair question? Or am I going fishtailing out a whole different subject than you wanted?
No, I think it's helpful. It is helpful.
Is that what you wanted?
Yeah.
Okay, I just want to make sure. Okay. There's a lot to do with the model with me holding it versus you holding it. Okay. There's a big distinguishing feature there. Okay. Almost all of this is those stereo diagrams where you like stare at it and you don't see anything. It's just a bunch of static until you like cross-eyed and stand on your head and poof, letters come out and say you're blind. Like that kind of thing is what's happening here. So this is one of the reasons why I do the model activity, which is one of the reasons why on Tuesday and Wednesday you might be like, Mike was getting a little up close and personal and like staring at me. Like that was the point, fudge, was to bring it into that alignment so that you and I are on the same wavelength and you can see the same system. Me moving the model gets close, but it's nowhere near as close because of that distance gap. Kind of, sort of? Okay. One of the other things that we'll kind of address, that I should explicitly address, okay, we've got our chair drawings. We just addressed that we have a difference between axial and equatorial. So knowing how to draw those and represent those can come in handy. First and foremost, when you look at your drawing, you should be able to quickly identify where your feet and your head are. One of the obnoxious things within our chairs is that when you look at a cyclohexane, there are 3 heads. Just like a fictional being, fictional beast, whatever you want to call it. Everybody see the chair there?
Yes.
Okay, that chair, where the red is our head, technically that's a substituent on it, but that's our head. Everybody got that? Okay. There is also the chair. Let's do that. There. Now where's the head?
The blue.
Now it's the blue. There's also the chair where the black is the head. Okay? And this adds a whole layer of complexity to this. Because I can be talking this way about this chair, and y'all over here are seeing the chair looking the other direction. Okay? Which is why you have to lock into that frame of reference. Even within this drawing, you can see other heads and feet. If you're starting to see those, look at something else. Stop looking at those. You need to get locked into this configuration. These 2 atoms are in front. Those 2 atoms are in back. This is your seat. Your head's there, your feet's there. Our 2 atoms in front, 2 atoms in back. Head is up, feet are down. Okay, always. Don't start saying this is a head. You're not. Oh, fudge. Fine. Don't start saying this is a head. You're right, but you've now shifted your viewpoint on that molecule so much, you're outside of the standard realm, it's going to be hard to answer any question because you're now looking at it from an entirely different viewpoint. Which means you're going to be oscillating back and forth. Kind of, sort of? Okay. So once we've locked in on what our head and feet are, we now need to understand our axial and our equatorial. Okay? Our axials. aim straight up and down. Okay? So all of those positions are our axial positions. The reference that we get are up, down, and what we're looking at is the point. Okay? If I look at the carbon where I want to place the atom, where is that point aiming? Is that aiming up or down? And for those smartasses that want to say it's aiming to the right, knock it off. Is it more up or down? Your only choice is those two directions. It's aimed up, which means axial is up. Our equatorial, then by definition, must be down. So I need to aim it away from the axial, but I get a lot of different range to go from. Okay, so in drawing that, you want to find parallel to the second bond away. There's my second bond away. I want to align with that angle. That's now my equatorial. And for people being, oh, you counted that way. Well, 1, 2, it's still parallel. If you've drawn your chair properly, it will always be parallel. It's neat. Right? That's kind of the beauty behind it. The big caveat is you had to draw your chair properly. Right? And so if you start getting sloppy in your drawing of your chairs and start drawing things incorrectly, all of those pieces fall apart. This is one of the reasons why it's important to draw the accurate three-dimensional model as best as you can. Okay? Let's say you're struggling. Okay? I want this green bond to be equatorial. Does that look like I've drawn it equatorial? This is interesting. The same table, vigorously no, like I was awful, and then yeah, that's equatorial. Okay, why do you think that's equatorial?
Well, if it's just based on the drawing, it's going out to the side. So that's what you were asking? Just based off the drawing? No.
Is that green bond going out to the side?
I mean, according to the drawing, no, but like... Is it
Okay, so I don't accept your explanation.
Like, I think I'm just thinking of it wrong, but...
I don't think it's necessarily that you're thinking of it wrong. Okay, I'll give you credit there. Why did you want to say no? You're talking through your arm. I can't hear you. You just know you don't like it. Okay. It doesn't look parallel to that second bond away, but what we're assuming is that you're struggling to draw these, right? Yeah. So you're going to struggle to draw them. How can you make extra clear that that green one is supposed to be equatorial?
Color them.
What's that?
Color them.
Well, it's colored. How do you know that green one's supposed to be equatorial?
Color the other one too.
So both of those are equatorial?
Well, no, that's not. No, I was going to color like the other one that was supposed to be parallel too.
Because we have that axle, we have to make that parallel.
Okay. If I want to make crystal clear, say to someone grading, that green line I'm drawing is supposed to be equatorial, what I might do would be draw the axial in. The axials are straight up and down. Those should be a little bit cleaner. By showing that red line there, that might be why you're saying, well, that green one's equatorial, because I can see the red one is axial because it's straight up and down. That allows me to say that's unambiguous. What else can you do? It's really simple. Do better. You can't do better. You haven't had enough practice. How can I make crystal clear that that green bond is supposed to be equatorial?
Right.
I'll look at it and be like, this is where it should be drawn. Okay, that's not equatorial. This is where it's supposed to be. But you've at least bridged that gap that I know what you're trying to do. You just suck at it. Okay? That's fair. Okay? I now have a reason to give you points. If you don't make that extra clear, I don't know. That makes it hard for me to give you points. Kind of makes sense? The blue one's appropriately drawn equatorial. Okay? And if we were going to draw the green one, it should be better drawn here. That's where it should be. Okay? But that relies on having a nice structure. Did you all draw a nice structure? I don't know. Some people are like, yeah, I'm awesome. Okay, that's great. Some people are like, I have a stencil. Of course it's awesome. And for those of you that don't know, you can buy stencils. Yes, that's absolutely acceptable. You can use a stencil on the exam. That's fine. Okay? Make sense?
Easy peasy.
So we now know where to draw all those. We've answered some questions both within smart work that are challenging on acknowledging axial and equatorial. We know where that energy difference is coming from within our Newman projection, how to visualize it, what becomes important within our Newman projection. I would say we've beaten that section to death.
Yeah.
And now it's just going to come down to practice, you working through and trying to really own that material. I could easily be wrong.
For the original structure, the bottom line, the bottom red line, would that represent on the feet?
Yes.
Okay, and then we just switched it over, that's why we went.
This is feet. This is head. I heard switched it over. There is no relationship between these.
I think I just meant the way they look, like the head's on this side compared to everything on that.
Yeah, because we're changing the direction of the head. Yep. Okay. That line, that bond you just referenced, axial or equatorial? Yeah. Equatorial. Good job. Okay. Kind of getting it?
Yeah.
Okay. Other questions?
RNS. You asked.
I did. Tempted to open up just a slideshow. When we're talking about RNS, it's very particularly referencing the orientation of space of four distinguishable groups around an atom. The vast majority of atoms that we would look at that is allowed four distinguishable groups would be carbon. So almost everything we're dealing with when we're talking about chirality and RNS is looking at a particular carbon. Okay? It can apply to nitrogen and phosphorus, okay? And it could theoretically apply to other things, but though carbon's the big one, okay, that you're going to see all over the place. It for distinguishable connections, okay, and it needs to be distinguishable bonds, which might be why you were giving me side eye potentially at the screen when you're thinking about nitrogen, and I might be able to talk about that. So what you would go through and do is find that atom that had four distinguishable things, and you have to assign a priority to those four different groups. That priority is based off of atomic mass, okay, which is a challenging statement to walk through. Most students will do it based off of molar mass of whatever the substituent is. It's not molar, it's a single atom. It's always an atom for atom comparison. Okay? And I'll pick out an example in a second. Okay? Once you've assigned your priorities, 1, 2, 3, 4, now you can go through and look at the arrangement of those atoms to say whether it's R or S. Okay? So it is purely structurally based. We have a structure, a drawing, and we now go through and make this assignment. Okay? We can't go into the lab and do an experiment to determine R and S. It doesn't happen. That's a whole nother ball game that's in the next unit. Okay? So once we've got it assigned, now what do we go through and do? Okay? We have to make sure the lowest priority is aimed away from us in our assignment. Has to be. And I'll show a quick example of that in a second. In this particular case, we can see it's aimed away from us because it's dashed. Now what I would go through and do is connect 1 to 2 to 3 as kind of a circle. As I do that, which direction am I turning? Clockwise. If I'm going clockwise, the assignment of that chiral atom is R. That's it.
So because you went
clockwise, 1 to 4, the comparison.
4 is not in the picture.
Okay.
What did I do? 1 to 2 to 3. That's how I went. Okay. Officially, 4 is not in the picture, because what you're supposed to do with this is redraw it, okay, by taking this molecule, let's see if I can pull this off, and we're going to kind of grab that too and kind of turn it that way a little bit. And if we do this, whoops. That's what we would see. Do those look like normal bonds? No, what are those? Wedges. Can I draw a structure like that? Like, no, that's totally not allowed. If we take a tetrahedral carbon, none of those bonds are in the plane. Every single one of them is coming at you, except for one, which is going directly away from you. When you assign R and S, that's where you're supposed to look. Okay? When I initially set it up, 4 was already aimed away from us, so I didn't have to do this special rotation to get it into that alignment, because I'm already in that alignment roughly, and I can run that circle count. Okay? But officially, you have to make that shift. So if we look at that drawing, I believe you started here with 1 and 2 in the plane. Okay? 4 is back here, 3 is here. And what we did was this. Okay? That's such a subtle change in the structure that that's not going to change any of our interpretations, and we're allowed to just do it straight from the drawing. We don't have to do a manipulation. Kind of make sense?
Yeah. So that's R clockwise, right?
R clockwise. Okay. What happens I should just draw it and hope for the best. In this scenario, think I've got that right? Whoop, yep. Green is straight up. 4, our white atom, is aimed straight at you. Red's in the plane and blue is coming away from you.
Yeah.
Okay? And if we go through and did this assignment, so let's leave that alone for a second, the model, and we run the same process, we go from 1 to 2 to 3. Which direction are we turning?
Clockwise.
Clockwise. So we would say
R.
R. But it's not. And the but it's not has to do with something that usually takes a little bit of work for me. But we'll try it. Which way is my hand turning? Okay, that was too slow. Which way is my hand turning?
To us or to you?
To you.
Counter.
Everybody okay with that? Is that really counterclockwise? I didn't change the direction of my hand, right? I maintained the same turning space. And yet you went from clockwise to counterclockwise, depending on the viewpoint, us or you. This is heavily dependent on viewpoint. So when we assign R and S, you must be oriented so that the lowest priority, that 4, is aimed away from you. If you do not have that proper orientation, you get it wrong. But it's a 50-50 split, right? So if you go through and look at it, and you realize 4 is aimed at you, what are you looking at it as? The complete opposite. So you could go through and assign, oh, that's going clockwise, so I call that R, but I'm completely opposite, which means it's gotta be S. Okay? And if we take our system, where do we place, right? There, you need to be looking at it from this angle. That's really hard to do when you're staring at that side of it. So if you take the molecule and turn it and switch it to that, we said green was 1, right? 1, 2, 3. Which direction are you turning your viewpoint? Don't give me my nonsense. Counterclockwise, which is?
S.
That's the assignment as done properly. Okay? When assigning R and S, you can check the internet, and I hope you can find a cheat for assigning R and S. Right? Every cheat I have attempted, other than I'm just looking at it perfectly backwards, gets me a 50% success rate. Right? And if you aren't great with numbers, that's okay. We only have R or S, which means just guessing is 50%. So the fancy cheats that the internet spits out are guessing. Oh, we did such a good job because we got the answer right half the time. You just fucking guessed. You just made me do a bunch of work to guess. Right? The real challenge comes is what if you're in a system like this? If we're keeping hydrogen as our lowest priority, that white ball, is it aimed away from you? Nope. Is it aimed towards you? Nope. It's in the plane of the paper. So how do you assign R and S? You're going to have to do a manipulation of the structure, either on the paper or with the model kit, so that it's aimed away from you to run the assignment. Okay? Kind of, sort of? Okay. We're done. I'm going to try and talk more, but we're done. I'll try and remember to pick examples so that you can actually assign the differences between 1, 2, 3, 4 on Tuesday. But it's strictly atomic mass.
Actually, no, I was getting gone through the entire video, so maybe
It's strictly atomic mass. There are plenty of cases that it can make it more challenging. And this is going to sound weird, but I promise. Just keep packing up. But what I'll try and do is a quick example here. So if I wanted to assign the priority difference between these two, I will get a lot of students telling me this is higher priority than this.
right, it's heavier.
What's heavier?
The carbon or the oxygen.
Atomic mass.
Got it.
The atomic mass is carbon versus oxygen.
Oh,
It's the immediate atom next door.
got it.
Okay? Which then means oxygen versus carbon. Oxygen's the higher priority.
We didn't finish
That should be 1. That one should be 2.
Okay.
Right? But exactly what happens is you look at the entire piece. I don't care about the entire piece. This is why I very heavily emphasize atomic mass.
Got it.
Right? It does get more complicated because what if I encounter a system like this? So my first pass, carbon versus carbon, they have the same atomic mass. I can't tell a difference.
Yeah.
Okay? Well, but can I tell a difference between those two carbons?
No.
You're telling me you can't tell a difference between a carbon connected to a bromine versus a carbon connected to a carbon?
Oh, well, yeah.
So finding that difference, you say, I can't tell a difference, so you move to the next atom. Next atom, and you continue to ask that question until you find the difference. If you don't ever find a difference, then they aren't different, and that only counts as one unique bond.
Got it.
Okay? So in this case, what you end up saying is that the bromine has a larger atomic mass than the carbon, which then makes this carbon a higher priority than this carbon.
I need to go take my finals, or my pre-finals.